Hello again, everyone. Welcome to our discussion of section 5.2, where we will be talking about exponential functions and their graphs. This is a vast area of mathematics, and we will just introduce the topic to you, as well as the other types of functions we've talked about before, right? So far, we've talked about quadratic functions, absolute value functions, square root functions, and of course linear functions, but we haven't yet talked about exponential functions. Before we get into the details of that, I'd like to remind you to please skim through this section 5.2, take 30 minutes or 45 minutes max to read through the section, and then attend the class and watch this video and take notes of anything that might be important to you or any questions that you might have. Then review your lecture notes and then go back to the solved examples in your book and solve those problems on your own without looking at the solutions given in the book. Only after you're done, compare your solutions with the ones in your book. And please repeat that process with the problems I go over in this video, so that by the end of the video, you will have practiced all these problems again without having looked at the solutions that I gave. Okay, of course, comparing your solutions with mine. And then please complete all the homework for this and other upcoming sections by the due date. And please, of course, spend half an hour each week, just 30 minutes each week, to review any of the previous sections we've covered. Okay. Having said that, then what are the exponential functions and why do we call them exponential functions? So far, I'm sure you've noticed that all the x variables or independent variables that we've been solving for, they were on the same level as the variable which was the independent variable. In other words, y or f of x, these were at the same level. But with exponential functions, the variable, the independent variable x, which is usually x, appears as an exponent, right? So far, we always had a number in the exponent. But when you have a variable, and the independent variable in the exponent, as you can see here on the screen, notice that the variable x is appearing in the exponent of these functions. So for this reason, we call these exponential functions. So the graphs of exponential functions are one of two categories. Right, for example, with respect to quadratic functions, do you remember the graph is always like a right side up bowl or an upside down bowl, otherwise known as a parabola, right? The square root, quadratic functions, not square root, but quadratic functions always plot as either a right side up bowl or an upside down one, or as a parabola. Here, exponential functions fall into two categories. Either they are a rapidly growing function, and their graphs represents that behavior, a rapidly growing function, or a rapidly decaying or declining or decreasing function. Okay. For example, a lot of natural, economic, or even financial data might have this pattern. For example, when scientists look at the population of a colony of bacteria, usually a colony of bacteria have an exponential growth rate. That means you put two of them together and all of a sudden, within half an hour, you have millions of them. Okay, so that's exponential growth. It rapidly increases. At the same time, there are situations where some phenomena may have rapidly declining pattern of decreasing. So rapidly decreasing pattern. So there are also quantities like that. For example, if we have a viral infection, and if there is a good medicine that treats it, then the medicine will rapidly decrease the number of viruses in the body of a patient. Okay, and this kind of pattern, exponential growth or decay, has been used in science, in business, economics, and financial data, as well as looking at the decaying behavior of nuclear material, such as uranium-235, I believe. It has an exponential decaying pattern in the rate it loses its radioactivity. So you can see here on the screen some graphs of exponential functions. So for example, y equals 2 to the x power has this graph. Again, we're reading graphs from left to right, so look how it is rapidly increasing this way. And y equals 3 to the x, notice the base is 3, and so it's higher than 2, so which means it's even more rapidly increasing than this one. Notice how steep this graph is, the one for 3 to the x. And here there's an interesting pattern is happening. If you compare the bases of these exponential functions, I'm talking about 0.532. There's a very significant pattern here. The pattern is this: if the base of an exponential function is larger than 1, just like the 2 to the x power and 3 to the x power, if it's any number larger than 1, you're going to have a rapidly growing exponential function. If the base of the exponential function is any value between 0 and 1, not including 0 and 1, but between 0 and 1, then the exponential function is a rapidly declining function. So this function, it has 0.5 is some number between 0 and 1, and look at the behavior. It is rapidly declining, right? And you could predict that even without a technology, just by noticing the base. What value does it have? If it is between 0 and 1, then it's a declining function. If it's larger than 1, then it's a growing function. Okay? So this one is actually asking us to answer some question. It says exponential functions can be either of decaying, i.e. decreasing type, or growing, i.e. increasing type. In the graphs below, identify which one is of decreasing type and which one is of increasing type. So we read graphs from left to right. Therefore, this one is decreasing, right? It's a decreasing exponential function. How about this one? This one is from left to right, it's increasing, right? So it's an increasing exponential function. And this one, the dashed one, y equals 2 to the x, it's of course increasing from left to right, right? So increasing. Okay, so underneath it we have another set of graphs. I guess they want us to do the same thing. I guess that's what my intention was as I put this on the on this page, but of course I didn't make that clear. But yeah, let's do that. So this one, what do you think this is? It's from left, read it from left to right, going this way, right? It is increasing. So this is increasing. How about this one? read it from left to right, it is decreasing. And this one, read it from left to right, it is increasing. And this one, read it from left to right, it is decreasing. And this one, read it from left to right, it is decreasing. Like that. Okay. All right. So oftentimes, experience tells me that a lot of people have difficulty calculating exponential values. So they know where the numbers go, but when they enter it in the calculator, they have difficulty calculating it. So I put together these 3 simple calculations for us just to make sure that every one of you can use your calculator to calculate this exponential function, which we have here, that one. Okay? Let's calculate it together. So you have your own calculator. I have my own here, which I will place here. Let me see how I can put this so you can see it on the screen. I guess this would be good enough, like that. I think that would be good enough. Okay. Maybe a little bit higher, like that. Okay, that's better. All right, so here we want to evaluate this function at x value equals 1.5. So as I calculate this, please make sure you use your calculator to see if we get the same numbers, okay? So on my calculator, the e to the x function, the e is the natural exponential function. We will get to it on the next page shortly, in a few minutes. But it's a very famous function, very important mathematical function. So it's called natural exponential function. And it's so important that it has its own button on the calculator. So on mine, I don't know how well you can see it on the screen, but it's barely visible. It's a light blue right on top of this key, which is the natural logarithmic function. So because the two are connected. So if I use the second button, I can activate my e to the x function. That's what activates this e. Like I say, on the next page, we will get to what e is, but it's such an important value that your calculator should have it stored as part of your calculator. So you shouldn't have to enter it. Okay? So find that key. Find the key in your scientific calculator that activates to E. Okay? You want to activate it. On mine, there it is. Okay? So I'm going to activate it like that. Do you see it? It says e to the power. And then I'm going to enter minus 2x, right? Minus 2x, in this case, in part A, x is 1.5. So minus 2x would be minus 2 times 1.5. And I'm going to close the parentheses. Okay? Do you see how I entered that? Okay, now hit enter. If you did everything correctly, then we should have this result on our calculator. Do you have that result? If not, look back at what you did wrong. Okay, this is the result we want. So let me write it down. It is 0.0497. I'm going to round the 8 to 9. Okay, so that's that. Okay. Now we're going to calculate this quantity. That function at x equals negative 4. Okay, once again, I'm going to activate my e function, the E button on my calculator, then minus 2 times x would be minus 2 times minus 4. So minus 2 times minus 4, close parentheses. Hit enter. Do you have that result? If you have that result, everything is good. If not, please look back at what you did that gave you a different answer. But I'm going to round that number, so it'll be 2,980 point, I'm going to round the 5 to 6, 96. Okay? You see that? All right. Now that one, that's the same function at 0.5. So I'm going to enter, when I'm going to enter this, I'm going to enter it as minus 2 times 0.5 for that one. So again, I'm going to activate the E button, and then inside I'm going to put minus 2 times 0.5. That value, right? So I'm going to round that to, let's say, I'm going to round this 7 to 8 because of the 9 after it. So 0.3678 and then 8, right? The 7, I rounded it to 8. Okay. I hope just going through this helped you figure out where the buttons are and the E button and how to input that calculation. All right. So the natural exponential function, which is that e to the x, let me highlight it. So this is the function, and it's called the natural exponential function, that one. Okay, and the e part is what we had in our calculator. So e is an irrational number. It's like square root of 2, a square root of 3, all these irrational numbers. E is another irrational number, and it is equal to this quantity, 1 plus 1 over n to nth power, where n is anything that goes extremely large. So in calculus, this is a notation used in calculus a lot, and n arrow infinity means as n becomes very large. That's the interpretation of that. So if you calculate this formula, if you have free time, and if you have 10 minutes free time, and if you are interested in this, just use growing values of n and calculate this formula on the right. So pick n equals 100, calculate this. 1 over, that is 1 plus 1 over 100 to n 100th power. Then choose 1,000, then choose 100,000, 1 million, 10 million, and on, as you increase n to be very large, maybe 1 billion, you see that the value of this quantity converges. It converges to a certain value. And that value, that irrational value, these are the first few numbers of it. It converges to something like this. As n becomes very, very large, the value of that quantity converges to this. And of course, you see dot, 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 because this is an irrational number, meaning the digits that come after the decimal will never end. So, but the first few digits are like that. And you can see that, you can verify that as you increase, start n with numbers like 100 or 1,000, and then increase it to, or even 10. Start it at 10, and then increase it to 100, 100,000, 1 million, 1 billion, and see what happens to the value of that quantity. You will see that it will converge to this value. And the larger the value of n, the closer you are to this value. Okay? And that e is that value which is stored in our scientific calculators. All have it. Okay, I'm not sure. Maybe even the business calculators have it too, because this function has many applications in the business and financial world. Okay. So in this picture or graph, you can see that whole thing is summarized. So I have summarized the function and its graph. That's this one. I mean, in the original PDF file, I believe this was in color, but when you print it, it's not. But it's comparing the the graph of the natural exponential function. Let me highlight it. So, which is the middle one. It's the middle line right there. With two other graphs of two other exponential functions, one being y equals 2 to the x, the other one being y equals 3 to the x. Okay? It's just making a comparison side by side, because as we mentioned, E is 2.71828, right? So 2.7 is somewhere between 2 and 3. So as you can see, the graph of this is between the graph of y equals 2 to the x and the graph of y equals 3 to the x. Okay? And this is again that same formula that we had up there, and this is the value it converges to as n becomes extremely large. Okay? So here on the second exercise here for us, it says graph each function by substituting and plotting points. So it says manually basically graph this. Okay, so that shouldn't be too hard. If we do a table of values here, a small one, right? So let's say these values are x and these values are f of x. I'm going to pick some easy numbers. I'm going to pick 0 for x, which means f of anything to 0 power is equal to 1. Then I'm going to pick another easy number, x equals 1, 5, another easy number, 25, and so on. Okay? And then on the negative side, we can pick something on the negative, but notice that with negative powers, this number becomes very, very small. So if we take 5 to negative 1 power, right? So 5 raised to negative 1 power. See, 0.2. So let's do that. So minus 1.2. Let's pick 5. Let's calculate 5 to negative 2 power. 5 raised to negative 2 power. Look at that, right? So the point being, as you pick more smaller and smaller negative numbers, you get closer and closer to 0. Okay? That's in fact what is happening in this graph up here. Notice on the negative side of x, as x values get smaller and smaller and smaller, this line appears to be approaching y equals 0, which is perfectly correct, because the exponential function will never be 0, but depending on the value of x you choose, such as these smaller and smaller negative numbers, the value of the function will get very, very close to 0, but it will never be 0. But I think these few digits that we randomly picked and calculated should give us enough points to draw the graph for this exponential function. Again, this is an exponential function because it has a variable in the exponent. So 0, 1, I'm going to take each one of these little squares as a 5 increment. So this would be 5, and this would be 10, 15, and so on. And on this side, it will be negative 5, and so on. Then 5, 10, and 15, and so on. So maybe that wasn't the best choice for incrementing my axis, but it's okay. So 0, 1 would be somewhere here. 1, 5 would be somewhere here. All we need is just to get a rough idea where this curve is. That's all. And first of all, we know it's a growing exponential function, right? Let me actually write that down. So because of this, because of the base, because of this base, we know that 5 is greater than 1. Thus, we have an increasing exponential function. Okay, an exponent. So we know this line is going like that, right? Increasing. We already have an idea. So 2, 25, that would be way up here. So that's, if that's 15, this would be 20, and this would be 25. 2, 25 would be somewhere here. So wow, this is a really steep growing exponential function, right? As it turns out. And then on this side, -1 is equal to 0.2. So let's say x equals -1, right? So it's on this side. And then -2 is near 0.04. So if I graph this, I'm going to use my red ink to do it so it shows better. So the line is coming from here, then it goes through these points, and then it shoots up right like that. Growing very, very rapidly. Okay? And on that side also it goes this way and that way. Okay, so that's a rough sketch of that. Then we have this function to graph. Here something interesting happens, right? Because the power, the exponential function, the power has a minus in front of it. So what do you think that will do to the graph of the function? Think about it before we actually do this. Do you think what that will do? See, the base of this exponential function is greater than 1, right? So we would expect this to be an increasing function, just like the one that we just did. But because of this minus in front, it's actually a declining exponential function. So that's the effect that that minus in front will have on the graph of this specific exponential function. Not always this will be the effect. There are other parts of the function that should be looked at, and they may come in handy in determining that determining the final behavior of the graph on the plane. But in this case, because this 3 is positive, if it was -3, the story would be different. But because it's +3 raised to -x power, so the impact of that minus in front of the x is that it'll make this function a declining function, a rapidly decreasing function. If that minus wasn't there, if we had 3 to the x, as you saw before, so as a matter of fact, let me bring it back. Remember this? Remember this? So if the power is positive x, then y equals 3 to the x is that one. So it's a rapidly growing function. But in this case, we have a minus in front, and the effect of that is that it'll make it a declining function. Let me write that down. So the negative in front of the x makes this function, or this exponential function, a declining exponential function. So it's that piece that's responsible for this. Okay. All right, so let's plot a few points. We know it's declining, so we know it's going to go this way, not increasing. So let's say, what would be some easy numbers? Well, 0 would be an easy number, so let me pick that. And then, of course, this would be 1. And then another easy number would be x equals 1. So that would be 3 to minus 1 power, or 1/3. 1/3 would be simply 0.333 something. Another easy number would be -1, actually. So when x is -1, minus 1 would make this +1. 3 to first power would be 3. Okay. So let's plot this to get an idea. We already know it's declining. All right. Let me actually underline this. Declining exponential function. Okay. So 0, 1 would be, let's pick here. I will pick each box, little box, as one increment. So 0, 1 would be there. 1, 1/3 would be here, roughly here. -1, 3 would be -1, 1, 2, 3 would be here. I think this is enough for us to graph this, right? We know it's declining, and these 3 points give us a pretty good idea how this line should go, how this graph should go, right? So let's draw it. So this line is coming like this, and it's going through these points, and then does that, and then it'll do like that. So it will not cross the x-axis, because this function value is never going to be 0. It's going to be extremely microscopically close to 0, the function value I'm talking about, this f of x. As you can see, it's getting closer and closer to 0 along the y-axis, but it will never be 0. It will just be very close to it. And that's why you see this asymptotic behavior. Okay? If you take Math 126, we'll talk more about asymptotes in that course. In this course, I'm not sure. Maybe it'll come up, but I don't think in this course we will go into it in a very deep way. I could be wrong, so we'll see in the upcoming sections. Okay, this one, next one, this is really interesting function, because so we have this, once again, we have a negative in front of the x, right? So we would expect a declining behavior, just like what happened here. Because E itself is greater than 1, right? It's 2.71828, something we mentioned earlier. On page 2, we said that E, the value of the irrational number E, and it begins with the digits, this, right? 2.718 something. So this number is greater than 1, so we would expect this graph to be increasing, but it's not, because we know that minus in front of the x makes this a declining exponential function. But hey, wait, because we have another thing going on here, which is this minus. So this minus, it's going to make this, again, an increasing function. So this function originally would have been an increasing function if it didn't have this negative x as power. With negative x as power, it becomes a decreasing function. But we have a negative in front of this, so it'll make, the effect of this is that it'll make the graph increasing again. So the net effect, of what value this base has, and this negative in front of the x, and this negative in front of the e, the net effect of all these things at play is that this, we guess, it has to be an increasing exponential function. But as they say for this problem, let's plot some points manually and see where this takes us. So x and f of x. Okay? Like that. All right. So let me pick some easy numbers again. Easy numbers would be 0 for sure. So anything to 0 power is 1. 2 minus 1 is 1. Right? This whole thing, if x is 0, this whole thing reduces to 1. 2 minus 1 is 1 again. So that was an easy choice. What else we can choose that would be an easy? Let's see. Let's pick negative 1. Right? What about negative 1? Negative 1 would be then minus 1 would be positive 1. So e to the 1, e to the first power, that would be 2 minus e to first power. What do we get? Let me calculate that. So if x is negative 1, I'm calculating what f of x would be, right? So 2 minus, I'm going to activate my E button right there, and then minus x. So, or minus 1, right? Because I picked minus 1, so minus x would be minus 1, which is positive 1. So we have minus 0.72, let's say. Let's round that to 0.72. So negative 0.72. Okay, so once we ventured into negative x value territory, our function value became a negative number as well. Okay, that's the significance of that. I wonder if we plot these 2 points, because this is graphing this would be a complicated thing as opposed to graphing it with a computer. But let's plot these 2 points, because of these 2, because of minus e minus x, this is an increasing exponential function because of those things, because of a combination of that. Increasing exponential function. Okay, so 0, 1. These numbers are very small, so I'm going to pick my increments a little bit large. So let's pick this as 1. Every 2 squares, little squares, as 1 increment. So 0, 1 is that, 0, comma 1. And then negative 1, that would be here, and negative 0.72. So somewhere here. Okay, so this would be negative 1, negative 0.72. Okay, so let's get another third point. So if we have, because this isn't enough, let's get maybe positive 1, x equals positive 1. So if x is equal to positive 1, then we have, let's calculate that number. Right? So for x, we have 2 minus that, minus, if x is 1, minus x would be minus 1, right? So minus 1. So it's a positive number. Let's say 1.6, right? So 1.6. I rounded it to 1 decimal place. So that, where would that plot? That would plot 1 and then 1.6. So it would be right here someplace. Right there. Because this would be 2, sorry. This would be 2. Okay, that would be 2, and this is 1, this is negative 1, that's 1. So 1 comma 1.6 would be that point. And then let's get another negative value here, because we need to know a better idea about where this line is going. So let's say negative 2. Negative 2. So if x is negative 2, that would be e to positive 2 power, right? So 2 minus e to positive 2 power, positive 2, right? So negative 5.4, let's say. Let's round that to negative 5.4. Negative 5.4. Okay, let's plot that. So we have negative 2 would be here, and negative 5.4 would be way down here. 1, 2, 3. It would be way down here. Way down. Let me just put it there. It's going to go off the page if I went with the increments that I picked, or nearly off the page. But now we have a pretty good idea of what's happening, right? Maybe another one. Maybe let's do a 2 as well. X equals 2. When x equals 2, what happens? What is the y value? Let's calculate. So that would be 2 minus e. If x is positive 2, then it would be e2 minus 2. So 1.9, let's say, right? Let's round it to 1.9. 1.9, roughly. So 2 comma 1.9 would be roughly here. So do you see there's a flattening going on here? I mean, it's increasing, but from here to here, look at the jump. But from here to here, it's not much of a jump. It's still increasing, but not at the same rate as we were on the negative side. So we can draw this line like that. Okay, let's draw it like that. It's still increasing. It doesn't curve back down, but it's increasing, but at a much lower rate after we cross over to the positive side of the x-axis. Before that, when we're over the negative x values, look how fast the function was coming up. But all of a sudden, right after x values became positive, then it's kind of flattening. It's still increasing. This is an increasing function, so it will always increase. But once we switched from negative to positive x values, the rate of increase became much less. That's what this graph is showing, basically. Okay, but it's going to look like something like that. All right, so another graph here. This is a throwback to piecewise functions. Remember that? When we did that, I used my ruler. So let me once again grab my ruler and my pencil. If I remember to bring those with me. Yes, I did. I have my pencil and my eraser. Remember when we were graphing piecewise functions, how I suggested that you should do it? You should, when you start graphing piecewise functions, these are the conditions. What you see, these are the conditions on the domain. So if x is less than or equal to negative 3, this is the function value, 4. If x is between negative 3 and 0, this is the function. If x is greater than 0, this is the function. So when you graph originally the piecewise functions, ignore the conditions. So you pretend that they don't even exist. Then you graph each of these as if the other ones didn't exist. So you say g of x equals 4. What does it look like? So you draw that. And then what if x squared minus 6? What would that look like? And e to the x, what would that look like if the other ones didn't exist? You draw all of these lightly with a pencil. When you're done drawing each graph individually, then you go back and then, based on the condition, you erase portions of the graph that must go away, and you keep the ones that match these conditions on the domain. Okay, so let's do that. That's why I grabbed my pencil and my eraser, because I'm going to draw everything but lightly, and then I'm going to start erasing when I look at the domain later in a few minutes. So if the function g of x was equal to 4, and I'm going to pick 1, 2, 3, 4, so that's that, then it looks like a horizontal line. I'm going to draw that lightly with this pencil, right? Like that. You barely see it on the screen, and you should, because that's not the final piecewise function. Okay, let's graph x squared minus 6. We learned about transformation of functions, right? So this should not be very difficult for us to graph. It's simply x squared itself has its vertex as at the origin, but this is x squared minus 6, so it's shifted down 6 units. So 1, 2, 3, 4, 5, 6, right there. And the y-intercepts for that, the x-intercepts, let's find where those x-intercepts are. Okay, those x-intercepts, so for g of x equals x squared minus 6, the x-intercepts are 0 equal x squared minus 6, x squared equals 6, right? I just moved this negative 6 to the opposite side. And then it doesn't matter if 6 is on that side or this side, as long as they're on opposite sides. And then x is equal to square root of 6. Is that correct? Is this x squared equals 6? Is that correct? X equals the square root of 6. Is that correct? What do you think? Is it missing something? It's missing something. What is it? It is plus or minus. Right? Here, x does not represent distance. So we must have both positive and negative pieces. And by the way, what is the square root of 6? It should be 2 point something, right? But let's figure it out, because I'm going to have to plot it. So square root of 6, 2.44, let's say 2.4. Right? I'm going to round it to 2.4. So x, or x-intercepts, well, let me first write it. So x equals plus or minus, I should say almost. So this 2.4, this means almost. 2.4, so then the x-intercepts are minus 2.4 comma 0, and positive 2.4 comma 0. Okay, I'm almost off the screen there. Okay, so now it's better. So now let's plot this with my pencil, of course. So this was the y-intercept. That was easy to get, right? For x squared minus 6 piece, that's the y-intercept. The x-intercepts are these. Those are the x-intercepts. So let me make sure that I identify that. These are the x-intercepts. And so minus 2.4, if this is 1, 2, 3, minus 2.4 would be somewhere here. And positive 2.4 would be somewhere here, because that's 1, 2, and 3. So that's positive 2.4, and that's the y-intercept. So I'm going to lightly draw the graph of this, x squared minus 6. So it would look like something like that. Okay, very lightly, because we're going to erase a lot of this. Okay, then let's graph g of x equals e to the x, the function that we're learning in this section about, right? The natural exponential function. We need to graph that. So the we know this function can never be 0. We know it's an increasing function. And we know that the y-intercept is going to be at 0, 1. Right? So for this function, let me write it here. For y equals to, or g, sorry, g. So for g equals e to the x, when x equals 1, g equals 1, right? So the y-intercept is 0, 1 is the y-intercept for this function. And we know it's an increasing function. So if I plot e to the x, so this is 0, 1, so it'll look like this. Like that. Okay. So now that's roughly all three functions graphed at the same time. Now we go back to the domain and erase what we should according to these conditions. So we are told that if x is less than or equal to -3, that would be 1, -1, -2, -3. If x is less than or equal to that, then the graph of the function is g of x equals 4, right? Equals to that. So that means if I go up at that point right here, I'm going to erase that. And the only function at that point is that. Like that. That's for all x values that are equal to or less than -3. That's the behavior of the function. For x values between -3 and 0, then we have, so at 3, 9 minus 3, 3. Yes, 1, 2. So what happens at -3? At -3, positive 9 minus 6 equals 3. 1, 2, 3. So right there. So at -3, x cannot be -3 when we're with this function. So what I have to do here is put a hollow circle there. So it'll be at -3, it's going to be a hollow circle, but then the function will be the quadratic function. So I need to erase this exponential function, e to the x, like that, and also those lines, like that. So then this is positive 3, and it's a hollow circle. So this hollow circle is right above -3. Notice that with g of x equals x squared minus 6, x cannot be equal to -3. Therefore, we have a hollow circle. And then after that, we have the quadratic function that is taking shape. And it's taking shape all the way till x hits 0, which is right there. And I have to have another hollow circle there because x, with the quadratic function, x cannot be 0. So let me erase that and put a hollow circle at that spot. Okay, I'm going to erase all of this. And instead, I'm going to put a hollow circle right here at 0, -6. Okay, so it's going to come down and it's going to hit that and it's going to stop. So that's that piece. That curve represents this function over this interval. Okay? Once again, this curve with hollow circles at the end, because 0 and -3 are excluded from x, represent this curve over this interval. Okay? What happens after that? At x equals 0 and above x equals 0, anything positive, or x equals 0 or anything positive, the exponential function takes over. So that's that. So that's correctly a filled in circle. That's a filled in circle. These two are hollow. And then the rest of it is going to be that. So I need to erase all the other pieces of that. And the horizontal line as well. So that should go away. And all of that should go away. All of that. And that also. Like that. And the rest of this horizontal line. Okay, so then it'll be like this. Like that. Okay, like that. All right, so that's the graph of this piecewise function. All right? Okay. So next for us is the application. One of the most important applications of natural exponential function or exponential functions in general is in the context of business and financial calculations, economics, business, and financial. One of the basic but very important formulas in business or in finance is the calculation of compound interest, calculation of a deposit into an account, right? So you invest some amount, let's say $1,000, in an account that is earning interest at 2% compounded monthly, daily, yearly, semi-annually, whichever one of those. And you want to know how much money will it be in your account in, say, 5 years down the road, or 10 years down the road, or 15 years down the road. So when we talk about this subject in Math 126, we also talk about simple interest, and then we talk about compound interest, because you really should understand, but your book doesn't do that. Your book doesn't talk about simple interest. It jumps to compound interest. So let me say a little bit about simple interest, because that gives us a perspective on what compound interest really is. See, this is the topic for this that is discussed in this section. So the simple interest is this. If you have $1,000 and you invest it at, let's say, 5% for the next 30 years, right? So let's calculate how much interest you're going to earn, right? Let's calculate that. Let me grab a piece of scratch paper here. So this is what compound interest is not, right? So I want to talk about this because if you don't know what a simple interest account does, then talking about compound interest is meaningless. So first we need to know what a simple interest account is. So suppose we invest $1,000 at 5% for, say, 20 years. How much will there be in the account after this period? Okay, so if this is a simple interest, oh, I should mention, I forgot, well, we're talking about simple interest, but I should also mention 5% simple interest, right? Then how much will we have in the account after 20 years? Well, the simple interest calculation goes like this. You have $1,000 that you invest at 5%, which is 0.05. So this will be $50. $50 times 20 years. So you'll end up with another $1,000. So at the end of 20 years, you will have your original money, 1,000, and this is the interest. This is just interest. Just interest over 20 years. So 1,000 plus 1,000, and you get $2,000 at the end of 20 years, right? But notice what happened. The interest that your account is earning is always applying to the principal amount that you invested. So over the years, right, after year one, you're going to have $1,050 in your account. But that 5% isn't going to apply to $1,050. It's still going to apply to $1,000. That's why once I figured out what the interest is according to the principal money you invested, I multiplied that amount by 20. That gave me 1,000 for the 20-year period. That's simple interest. Your account is accumulating money, but this 5% keeps applying itself to the original money that you invested, not to the accumulating interest. Okay? That's the nature of simple interest. The interest amount, the 5% in this case, applies only to the principal, the money that you deposited, not to the interest that you're accumulating in your account. In other words, in a simple interest account, the accumulating interest in your account does not get interest calculated on it. Okay, that's simple interest. But, so every year for the 20-year period, every year the interest amount doesn't change. It's $50, $50, $50 for the entire 20-year period. Okay, but the compound interest is not like that. The compound interest is interest that applies to any amount that is in your account. If it's the principal, it applies to that. If it's principal plus interest from a previous year, it applies to that too. So compound interest is a much more rapidly increasing account than a simple interest account, right? Because the simple interest account doesn't give you interest on interest. It just gives you interest on the principal. But the compound interest, it gives you interest on interest plus the principal. Okay? All right. So here's the formula for it. This is the basic. The formulas for compound interest can get very complicated and lengthy, actually. Some of them are 2-3 lines long, but depending on the conditions on the account. But this is the most basic formula for calculating compound interest. So what do these variables represent? So in this formula, P is the principal amount. That's the money you deposit into an account. Okay? Then A is the future value, and I don't have it here. Let me write that down. So AT is the future value of whatever that is deposited after T years. Let me write after T years. Okay? So R is the annual interest rate converted to a decimal value. So many times when I give problems like this on an exam, people don't convert the interest rate as they plug it into this formula. So just like that example, 5%, they just put 5 for R, right? Which is not correct. That should be 0.05, not 5, but 0.05. So that's why I say R is the annual interest rate converted to a decimal value, okay? Then T is the number of years an amount was invested. And N, very important, N is the period over which the interest is compounded. So how many different kinds of compounding can we have for this formula? There are other formulas that will be different, but for this formula, we can have 5 different kinds of compounding periods. If N is equal to 1, that means the money invested, the interest on the money is being compounded annually, once a year. If N is 2, that means the compounding of interest happens semi-annually or twice a year. If the compounding of interest happens quarterly or every 3 months, then every 3 months per year, so N is equal to 4. And if it's monthly, N equals 12. And if it's daily, N equals 360. So why is N 360 for compounding daily? Why is it not 365? I know that in business calculations, 365 is not used. It's the 360 that is used for daily calculations in business. Now, you might want to ask one of your finance professors why that is. I don't know, but I do know that they use 360 for daily compounding of interest, not 365. Okay, so let's apply that formula or this technique to this problem. It says, suppose $500 is invested at an interest rate of 3.75% per year. Find the value of the investment after 16 years. Okay, that gives us a lot of good information, right? So in this formula, as you read this sentence, according to this formula, what are the different variables? So P, what is P according to this information? The P is the principal, right, which is $500. What about R? What is R according to this statement? The R is 0.0375, right? Not 0.375, not 3.75, it's 0.0375. What about T? What is T then? T is equal to 16, right? What about N? Well, they don't give us any information about N yet, but let's read on. So part A says the interest is compounded semi-annually. Semi-annually means twice a year, right? And we know that for semi-annual compounding of interest, N is equal to 2. So let me not write that here. So for this piece, N is equal to 2 because we have parts B and C too. So, all right, so let's plug in. Here we have the original formula, which is A sub T. I'm going to use the same variables there. Equals P times 1 plus R over N to N times T power. Okay, so P is 500 times 1 plus 0.0375 divided by N is 2, to 2 times 16 power, right? N times t. So please make sure that you use your own calculator to calculate this quantity. Please pause the video right now and calculate this using your own calculator. Before you see my answer, do that, because I've seen many people have difficulty. They plug in all the numbers in the right spot. Every number is correct. But when the time comes to calculating this, they make a lot of mistakes. So go ahead, calculate this and see what number you get, and then compare that with the result I'm going to get. Okay? Okay, I'm assuming you've done that and now you're back. So the way you would calculate this is from inside out. So first calculate the inside of this parentheses, which is 500 times. What I'm going to do is divide. I'm going to divide 0.0375 by 2 and add it to 1. That's what I mean when I say calculate the inside of the parentheses first. Just because 500 comes first doesn't mean that you have to start the calculation here. No. Calculate or observe the order of operations and begin from inside this parentheses. So we get 0.0375 divided by 2, right? Plus 1. What do we get? We get that. 1.1875. Okay? All right. So all of that to raise to that power. 2 times 16 is 32. Now, again, following the order of operation, don't multiply 500 by this and then raise it to that power. Raise this number to that power first. So 500, let's raise that number to power 32. Okay, let's see what do we get. So raise that to 32 power, we get 1.81202. When you deal with calculations involving exponential functions, always keep at the minimum 4 decimal places in the middle of your calculations. I mean, this is about dollars and cents, right? So when I get to the end of the problem, I'm going to round to 2 decimal places because it represents the cents in the amount. But in the middle of your calculations, you don't want to do that, because if you round too much in the middle of your calculations when you're using an exponential function, your final answer will be off by a large margin. So in the middle of your calculations, keep at least 4 decimal places. So what I'm going to do in this one, I'm going to actually keep 5 decimal places. So I'm going to keep 1.81202. Okay? So 500 times 1.81202. And of course, I'm going to write that down, but when I actually calculate this, I haven't erased that, right? I have not erased that number yet. So I can just multiply it by 500. Multiply it back by 500. So let me do that. So I'm going to multiply this quantity by 500. So we end up with $906, and now I'm going to round this to the nearest cent, which would be 1 cent. $906.01. Okay, $906.01. It's okay to round at the end like that, but not in the middle of your calculations. Again, with exponential functions, if you round too much too early, your final answer will be off by a large margin. Okay. All right, so this one, it says do the same thing, but this time if the interest is compounded quarterly. So the only thing that is changing here is n. For the interest compounded quarterly, what is the value of n? Compounded quarterly, n is 4. And that makes sense because quarterly, that means every 3 months, right? So let's calculate this. the same thing, but instead of n being 2, it's going to be 4. So let me do that. N now is equal to 4. So we still start with the 500. 1 plus, the interest rate didn't change. It's still 3.75%, but now we don't divide by 2, we divide by 4, right? That's n. Raised to 4 times 16, so that'll be 64, right? So again, just like before, don't start with 500. Observe the order of operations and start with inside the parentheses. So the first thing you should do is divide 0.0375 by 4 and then add 1 to it. Let's do that. Okay, 0.0375 divided by 4, like that, plus 1. So the inside of the parentheses is that I'm going to keep all of that. I'm not going to round anything there. So I'm going to write 500 times 1 point, there it is, right? 1.009375. Okay? To what power? 4 times 16, it is 64. Right? 64. Okay. Now we're observing the order of operations. So the next thing for us is not multiplying 500 by this, but raising this to that power and then multiplying back by 500. That's observing order of operations, right? Basic arithmetic. So 500 times, I'm going to raise, I haven't erased it, it's still on my calculator. I'm going to raise that number to 64, to power 64, right? Let's do that. So raised to power 64. So we have 1.817. I'm going to round, I'm going to keep 5 decimal places. So 1.81703 is where I'm going to stop. Okay? So inside 1.81703. But of course, even though I wrote that down on the calculator, I still have everything. So I'm not going to erase anything. I'm going to multiply this back by 500 times 500. There we have. We have $908, and I'm going to round that to 52 cents. Like that. Okay, a little bit off the screen there, like that. Okay, part C says, what about if the interest was compounded daily? Okay, so that's when interest is compounded daily, the N is 360, right? So let's redo this calculation with N equals 360. Okay, so then we have the future value is equal to 500 times 1 plus, the interest rate didn't change, so we still have 0.0375 divided by 360, right? That's N, no more 4 or 2, 360. To what power? To 360 times 16. Okay, so let's calculate this quantity. Again, we start with the inside to observe the order of operations. So we have 500 times, let's calculate that quantity. We want to know what is this value? 0.0375 divided by 360, right? And then add 1 to it, plus 1. Like that. So I'm going to keep everything until round the 6 to 7. Right? So let's do that. So 500 times 1.000100417 raised to what power? To this power, right? 360 times 16. What is that? 360 times 16 is 5,760. So raised to 5,760 power. Okay? All right. So now we have to then raise this quantity to that power and then multiply back by 500. So even though, notice that even though 500 comes first, the last thing we do is multiply by 500, right? Just to observe the order of operations. So 500, I'm going to raise this quantity to that power. Okay, so we have 1.000100417 raised to that power, 5,760. Okay, so we have 1.822096. I'm going to keep all the way to 6 and I'm going to round the 6 to 7. So we have 500 times 1.822097, and of course I haven't erased this, so I'm going to multiply it back by 500 times 500. So we have $911, and let's round this to 5 cents. 5 cents. Okay. Oops. Like that. Okay, now let's compare these values. All right, so we have now all of this on the screen. Notice when n was 2, when the interest was compounded semi-annually, we ended up with $906.01 in the account after 16 years. When the interest was compounded quarterly, we ended up with this much, and when it was compounded daily, we ended up with this much, right? A little more than $5 more than when the compounding was happening semi-annually for part A. So this small example is showing you how much impact compounding of interest has on growing the money exponentially, right? So this was just $500. But financial institutional investors that invest billions and billions into accounts that have interest rates of their own, then you can just imagine how much more that impacts the growth of large amounts of how much impact does compounding of interest have on growing large amounts of investments. Okay, all right. So I hope this made clear what exponential functions are, and thank you for persisting through another video with me. And for now, have a very nice day until I see you again next time.